How are you guys doing today? All right, nobody saying anything? Well, I got my stupid computer fixed. Apparently, my Surface Pen actually realized that. And it uses a battery that I did not know existed, so I had to go to 4 different stores yesterday afternoon to find one, but we should be good to go today. So we're going to start by looking at the in-class assignment 16 again, but from a slightly different perspective. So I hope that you guys actually watch the video. Let's see. So this is what we were trying to do yesterday before I realized I couldn't do it because my computer was misbehaving. If we look at this first circuit, we observed that this resistor, this 5 kilo ohm resistor here, placed between the inverting input terminal and ground for this particular configuration didn't do anything. So we're left with a feedback resistor here and what I'll call an input resistance here. And the configuration that we're looking at has the input resistance placed between our input signal and the inverting input terminal. So that makes this particular amplifier an inverting amplifier. And we can tell it, we can come to that conclusion, again, just by simply looking at where the input signal is placed. So the input signal is placed on the leg of the input resistor as opposed to directly to the non-inverting input terminal. For an inverting amplifier, as was covered in the video, we have, oops, I don't know what I did there, a voltage gain, AV, which is defined as V out divided by V in, is equal to negative the feedback resistance divided by the input resistance. So for this particular problem, we can use just that relationship and find that V out is going to be equal to V in, which is 5 volts, times negative RF, 10 kilo ohms divided by RN, 5 kilo ohms, gives us negative 10 volts with no circuit analysis whatsoever. That's why understanding these different negative feedback op-amp topologies is so powerful. Once you know them, you don't actually have to do any circuit analysis. You only need to use the input-output relationships. So if we look at our second problem, we can see that our input signal is not applied at the inverting input terminal anymore. It's applied at the non-inverting input terminal through a resistance. So that means that this is going to be a non-inverting amplifier. And the rule for a non-inverting amplifier is that the voltage gain, and here I'm going to define it slightly differently because our problem is a little different than a strict non-inverting amplifier, is the output voltage divided by the voltage present at the non-inverting input terminal. And that is equal to the ratio of 1 plus RF divided by RN. So to be very clear, I'll identify our feedback resistor, RF, and I'll identify our input resistor, RN. So we can easily determine what those two values are. Now we need to figure out how to find that voltage V plus. And we can do that by applying voltage division. So V plus is simply V in 0.25 volts times 80 kilo ohms over 80K plus 20K gives us 200 millivolts. Plugging this into our voltage gain equation and rearranging, we find that V out is equal to V plus 200 millivolts times 1 plus 24 kiloohms over 1 kiloohms. So that's simply 200 millivolts or 0.2 volts times 25 gives us positive 5 volts. Again, the amount of circuit analysis that we had to do here was very minimal. Really, the only thing that we had to do was take this voltage divider circuit and then figure out what this voltage was. Let's see, third problem here. So this is a more strict and straightforward non-inverting amplifier. Where we know, again, that AV is equal to V out divided by V in is 1 plus RF over RN, where here's our feedback resistor, here's our input resistor, and so we will get the expression V out is equal to V in, which is 5 volts. That doesn't look like much of a 5. Times 1 plus R over 1 kilo ohm. So we have two unknowns here, but we're given enough information to find V out. So we also know that V out is going to be the square root of the output power times the output resistance. And I got this from saying P out is V out squared divided by R out. And if I substitute in my numbers, let's see, square root of 0.025 times 10,000, 15.8113 volts. So if I plug this value in here, I find, using my numerical solver, that 5 times 1 plus x over 1,000 equals to 15.8113. Solve for x. Says I have an invalid domain error. I don't know what that means. Trying again. I get 2,162.26 ohms or 2.162 kilo ohms. So understanding these op-amp topologies can make analyzing op-amp circuits extraordinarily straightforward because we don't have to do any circuit analysis at all. So if you haven't watched the video on common op-amp topologies, I highly suggest that at least you view it before exam 2, or you're going to be wasting a lot of time doing unnecessary circuit analysis. All right, so now let's spend the rest of our time for exam 2 review. So who has any question regarding any of the practice problems from the old tests I put up or homeworks or anything like that?
Just real quick before we get into that, did you just say that the op-amp stuff will be on exam 2?
No, it will not. It will be on exam 3.
Okay. Okay, thank you.
All right, questions regarding exam 2 material?
I just have a question. I guess more of the fundamental aspects of it. What
Okay.
are um like okay, so let's look at the winter exam.
All right, let me pull that up real quick. Winter exam 2. All righty, which problem?
It'll be 3 and 4. It's those problems where uh they they ask like what equation goes with the what the question's asking.
Okay. So let me scroll up here. So problem 3 on the winter test asked which of the following expressions may be used to determine the power absorbed by a capacitor. So power absorbed by a capacitor. So let's consider a simple capacitor. Like so, has a value of C, and there will be a voltage drop VC as a function of time over it, and a current IC of T as a function of time flowing through it. So the power absorbed by the capacitor, by definition, will always be the current flowing through the capacitor multiplied by the voltage drop over the capacitor. 100% of the time, P is equal to I times V, for sure. Now, in a capacitor, we also know that IC of T is equal to C dV by dt. If we substitute this relationship into our P is equal to I times V relationship, what we're left with is C VC of T times the derivative of VC of T with respect to time. So these are the two equations that might show up on your exam.
Okay, and
There's also an integral-based relationship as well that we could technically substitute in, but I've never seen that done in a textbook or anything, so I don't bother doing it.
and then I guess just for the next one, for the inductor,
So which of the following equations correctly relate current and voltage in an inductor? Alrighty, so I believe, so for an inductor, as a value of L, there's some voltage drop VL of T across the inductor and some current IL of T flowing through the inductor. From Faraday's law of induction, we know that VL of T is equal to L di by dt. So that's our first relationship. And we can, if we multiply both sides by dt and integrate, we also get IL of T is equal to 1 over L integral from, two ways we can put this, negative infinity to T of VL of, let's call it tau. No, let's call it X. dx. But more commonly, we would see this as 1 over L integral from T naught to T of VL X dx plus IL at T naught. So this is the fundamental relationship that governs the voltage current relationship in an inductor. And then this is just an alternative way of expressing that exact same relationship. But we would use the second one when we know what the voltage is and we're trying to find the current, and we use the first one when we know what the current is and we're trying to find the voltage.
Okay. Right. Thanks. Thank you.
Yeah, x in the bottom bit here is just a dummy variable for time. So in the it looks like in the answers that I have, I'm using t prime as a dummy variable as opposed to x, but it doesn't particularly matter what that dummy variable is.
Yeah. Um, I mean, I'm sure I'll figure this out within the next couple of days. But and you said a couple classes ago that we'll be learning something that we don't even need to remember this. But when you add inductors together in series, they're like resistors, and then when you add capacitors in series, they're parallel.
Okay, so inductors in series add like resistors in series. Inductors, let me write all this down. So inductors in series add like resistors in series. Inductors in parallel add like resistors in parallel. Capacitors in series add like resistors in parallel. And capacitors in parallel add like resistors in series. So what I was alluding to, and we can't use it yet because we're not in the steady state sinusoidal circuits, is the concept of impedance. And what impedances are is the frequency domain equivalent of a resistance. And so we'll find that capacitors, resistors, and inductors all exhibit an impedance. And so they can all be treated like resistors in a steady state sinusoidal circuit, but we are not there yet. That'll be another about 1 week from today, I think. So for now, we have to apply these 4 rules in order to combine capacitors and inductors.
Okay. Yeah, it's good to know. I think that's permanently etched in my brain.
Okay. Any other questions?
I have one about the analysis, why am I drawing a blank on this? The transient analysis.
Okay.
Do you know like what the typical problems some students face whenever they get these problems wrong?
The thing that I see the most problems make an error on is computing the equivalent resistance of the circuit. So calculating the time constant. That's the point where I see probably the most problems.
Is that mostly because there's 2 equations and people probably get those 2 mixed up?
No, it's more so because they don't look at the circuit during the transient condition, and that's very, very important. And so what I mean by that is that if you're not looking at the circuit at t greater than or equal to 0 plus, so if you look at the circuit at t is equal to 0 minus, and you use that to compute your equivalent resistance, you're inherently wrong because the time constant is dependent on what the circuit looks like during the transient condition, not before that. So it's not forgetting that the time constant for an RL circuit is L over R, or the time constant for an RC circuit is RC. It's fundamentally computing that value for REQ is usually where I see the most errors being made.
So the equivalent resistance of O minus, that's the Thevenin resistance essentially,
Well, it's
right?
resistance either way. It's just we have to look at it during the transient condition for it to be part of our time constant. So for instance, let's look at in the winter exam, problem 26 through 30, I guess, that first transient problem.
Okay.
So I'm going to assume that you guys, well, we can actually work the whole thing if you want to. Doesn't bother me at all. But if
Well,
you
yeah.
just look at the time constant, we can do that. Whichever way is good by you is good by me.
I say we do it the entire one.
Okay, I can do that. Plus minus 8 volts. Oh, I didn't give myself enough room, dang. Hold on just a second. So hard to find. Select. There we go. Oh, what did I just do? All right, so let me redraw this again, but give myself actually the room that I need to do it. Inductor. A, this is B. So the switch is at A before closing, at B at T is equal to 0. 5 ohms, 10 ohms, 3 ohms. And this is 3 amps. All right. So this is our circuit. It is a total response circuit because when that switch closes, it's going to add the 8-volt source into affecting the inductor there. And we're going to be asked questions about our inductor current, IL of T, as well as this resistor current, IR of T. So the first thing that we're going to have to do, and the first question asks you, effectively, how does the inductor behave at T is equal to 0 minus? So at T is equal to 0 minus, our circuit is going to look like this. So let's see. So I'm going to have my 3 amp source in parallel with my 5 ohm resistor. My switch is closed at position A, so that 8-volt source is effectively open circuited, so I'm not going to bother drawing it. So I have my 10 ohm resistor here, my 3 ohm resistor here. Here's IR at 0 minus, which we're not asked for, but I'm just drawing it for the sake of argument. What do I do with my inductor for T is equal to 0 minus?
I forgot.
So at T is equal to 0 minus and T is equal to infinity, we are at DC steady state. So we need to use the DC steady state equivalent of our inductor, which means to a DC circuit, an inductor looks like a short circuit. Because if the current through the inductor doesn't change, let's go back up here and review this equation, right? So if we look at this guy right here, if the current through the inductor isn't changing, then the derivative of the inductor current is 0. So we have L times 0, which is 0, is equal to the voltage. Since we want the voltage drop to be 0, we replace it with a short circuit.
Okay.
All right, and here's my inductor current, IL at 0 minus. So before we get into the analysis here, we can easily observe that that 10 ohm resistor is in parallel with the short circuit that is representing the inductor. Correct or incorrect?
It's correct.
So that means we know that no current will flow through that 10 ohm resistor. Right? Since it's in parallel with the short circuit, all of the current will flow through the short. So what do you or any of you guys think would be the most efficient method by which to determine that current IL at 0 minus?
Current division?
Exactly right. So using current division, we can find that IL at 0 minus, which actually happens to be IR at 0 minus as well, is going to be 3 amps multiplied by, let's see, so I have 1 over 5 ohms plus 1 over 3 ohms, excuse me, in my denominator. It's the reciprocal of the resistance of the branches. What goes in my numerator here? Is it the branch I want or the branch I don't want?
Don't want.
So the don't want equation would be 3 amps times not the reciprocals. But for the reciprocal one, which works for any number of resistive branches in parallel, we do the one that we want, which in this case would be the 3 ohm resistance. So these two formulations are identical, but I would highly encourage you, let me move this out of the way, to get in the habit of applying this guy because it works for any number of parallel branches, whereas the one I'm about to outline in blue only works when you have exactly 2. So the one in red is more general, so it's the one that I prefer. So if we evaluate that, and I'll do it up here because I kind of ran myself out of room drawing all this stuff, I'll find the IL at 0 minus, so 3 amps times, let's see, (15/8), which is 1.875 amps. So if current division doesn't quite make sense to you, please go back and review the notes and video on current division. All right, so now let's look at the circuit at t is equal to 0 plus. So at t is equal to 0 plus, our switch is changing from position A to position B, which is effectively leaving a practical current source open circuited on the left-hand side that we're not going to need to deal with. And what we have now is, let me give myself room, our 8-volt source. Here's our 10 ohm resistor. Up here is going to be our inductor, and I'll ask you guys about that in just a second. Here is IR at 0 plus. So what are we going to do with our inductor?
Turn it into a current source?
Yes, we turn it into a current source that has the same direction as our inductor current and the same magnitude as our inductor current at t is equal to 0 minus. So that would be 1.875 amps. And we do that because the current flowing through the inductor cannot change abruptly. So whatever value and direction it had at t is equal to 0 minus, it must continue to have at t is equal to 0 plus. So how can I figure out what the current flowing through the 3 ohm resistor is here?
Could you do superposition?
You could do superposition indeed. So using superposition, we'll see how much we can fit here. With a voltage source on, current source off, this is going to look like somebody lives next to Barksdale, it sounds like.
Oh, sorry, that's me. I mean, so.
No problem. So this is what our circuit looks like at with the voltage source on and the current source off. That does not look like CS. So we could hopefully easily see that IR prime in this case is going to be 8 volts over 13 ohms, whatever that number comes out to be, 8/13 of an amp. Everybody good with that analysis?
Yes.
All right, with the voltage source off and the current source on, what we're going to have is our 1.875 amp source here's our 10 ohm resistor. Here is our 3 ohm resistor, and here is IR double prime at 0 minus. How could we go about finding IR double prime here?
Current division again.
Current division again. Yep. So IR double prime 0 plus, excuse me, is going to be 1.875 amps times 1 over 10 plus 1 over 3 down there, 1 over 3 up here. And just to make sure that my sign makes sense, the current's going in, so we expect it to split this way and this way. Okay, so I don't need an extra negative sign or anything there. So 442 amps. Here we had 8/13 of an amps. If we add those together, we get IR at 0 plus. Goodness, is IR prime plus IR double prime is 2.057 or 58 amps. Okay, now let's look at the circuit at t is equal to infinity. So at t is equal to infinity, we should have the exact same circuit that we have at t is equal to 0 plus, except that our inductor is now going to look like a short circuit. So that means we should have, here's our inductor. There's IR at infinity. So, excuse me, my question to you guys is, what's the value of IR at infinity?
8 volts divided by 3 ohms since the 10 is shorted out.
Exactly right. So 8 over 3 is 2.667 amps. Alrighty, and now comes the part where the original, or what I feel the part where most mistakes are made, okay? So we need to look at this circuit during the transient condition to find the equivalent resistance, right? Because the equivalent inductance is obviously, let's go back up here, 150 millihenries because there's only one inductor, so it can't be anything else. So I'm going to redraw the whole circuit. Where, let's see, we're looking at a dead network. So it's very important that we turn off our current sources and our voltage sources. So my off current source looks like an open circuit. Here is my 5 ohm resistor. Then I'm going to have effectively an open circuit here. Here's where my voltage source, sorry, was switched on, but I need it to be off, so I'm going to short it out. So there's my shorted out voltage source. Here is my 10 ohm resistor. Here's my 3 ohm resistor. And what I'm going to do is I'm going to look in through the open circuit terminals where my inductor would be placed. So this is the equivalent resistance that I'm looking for. The equivalent resistance seen by the inductance during the transient condition. So to be very, very clear here, this open circuit is because our current source is off, and this short circuit is because our voltage source is off. All right, so what resistance does the inductor see?
10 in parallel with 3.
That's right. So REQ is 10 ohms in parallel with 3 ohms. So that's 10 ohms times 3 ohms over 10 ohms plus 3 ohms is 30 over 13 ohms. So for this one, I don't think calculating the equivalent resistance was particularly difficult, but if we had erroneously did this at t is equal to 0 minus, our circuit would look very different, right? So we would still have that short circuit where our voltage source was, but instead this switch would be closed. Oops. And the equivalent resistance would look like 10 in parallel with 8, which is definitely not the same as 10 in parallel with 3. So it's very, very important that you look at the circuit at t is equal to 0 plus in order to calculate your equivalent resistance, or you're going to get it wrong. So now we have all the different information. We could throw it into the generic equation and blah, blah, blah. So I think I've done enough on this particular guy. Any other questions? All right, so to be clear, your exam is going to cover lectures 9 through 15. So that means you're going to have questions regarding Thevenin and Norton equivalent circuits, both with and without dependent sources. You're going to have questions regarding inductor current and voltage relationships, which we've talked about, capacitor current and voltage relationships, and then you are going to have transient analysis problems. There will be 2 transient analysis, full-on transient analysis problems that you will have to analyze. Each one will be broken into 5 sections. So analyzing the circuit at t is equal to 0 minus, analyzing the circuit at t is equal to 0 plus, analyzing the circuit at t is equal to infinity, determining the time constant, and then evaluating the waveform at a particular time. So 10 of your 35 questions will be on transient analysis specifically. I want to say roughly 5 of your questions will be on Thevenin and Norton equivalent circuits. So that counts for 15 of your analysis questions. So the remaining 10 questions will be about capacitor and inductor current voltage relationships. So there will be a graph problem that you'll have to analyze. There'll be a mathematical expression that you'll have to manipulate. And then there'll be probably a DC circuit that you have to find the energy stored in, and likely a circuit similar to homework 12 problem 5, where you'll have an exponential source, a capacitance, and an inductance, and you'll need to be able to apply KCL and or KVL in order to figure out some quantity. All right, last chance for questions.
Yeah, I have a question about the first exam.
Sure.
Did you ever figure out if there was going to be a curve, or is there none?
So there was one problem whose correct response rate, I think it was number 11, was a little lower than I would have expected, but I double checked my math and I seem to be correct. I'll look at it again, but that's the only one that's potentially up in the air. So at a maximum, your score would improve by 3 points.
Thank you.
Mm-hmm.
Thank you for your help today, Professor.
No problem. Any other questions? All righty, I'll see you guys. Well, I guess I won't see you on Thursday since we won't have class. So I'll see you guys next Monday afternoon, but your exam is still Thursday evening. All right, catch you guys later.